This video is about entropy. Entropy has the symbol S. And the change in entropy is, as usual in this chapter, delta S. And if you see delta S with a little circle up here, that's delta S under standard conditions, which you will recall is 1 atmosphere of pressure and 25 degrees Celsius. Now, entropy means disorder. Disorder. Everything in the universe heads toward least energy and highest entropy. Think about a deck of cards. If you take a deck of cards that's ordered in suits and ace through king and you throw it up in the air, it is not going to land in that nice order. It's going to be disordered. And the reason for that is because there are more possibilities of disorder than there is order. That's something called Boltzmann states. Boltzmann states. And that just means all the possible ways the cards can rearrange themselves. And as you can imagine, there's a heck of a lot more different ways the cards can arrange themselves in disorder than in order. That's why the universe heads toward disorder. Let's think about this in terms of something we can understand. Here is ice. It's very ordered. It's very logical. All of the molecules are stuck together, rigidly bonded, and they don't move, except for a little vibrating. As the temperature warms up, I get liquid. Look how much more disorder there is. Look how many more ways there are for those molecules to rearrange themselves. So liquids have a greater delta S, a greater disorder than solids. And if I keep raising the temperature all the way up here to the boiling point, now I have a gas. Look at the molecules of a gas. That's even more disordered. So a gas has a great deal more entropy than a liquid. Let's look at a couple of examples here. Here is a balanced chemical equation. 2 moles of NO gas plus 1 mole of O2 gas goes to 2 moles of NO2 gas. Now, if you think about what we just talked about, gases are really high in entropy because they're really high in disorder. On this side of the equation, we have 3 moles of gas. On this side of the equation, we have 2 moles of gas. The moles of gas has decreased. And if the moles of gas has decreased, that means there's less possibilities for Boltzmann microstates. There's less ways in which the molecules can rearrange themselves. So entropy has decreased in this one. Decreased. In this one, on the other hand, CO2 solid goes to CO2 gas. I have a solid, that very rigid lattice pattern, going to the random movement of a gas. Here, entropy has increased. There's a lot more disorder going from a solid to a gas. Now let's think about sign. This is very, very important. Delta S increasing is positive. If there is more disorder, delta S is positive. If delta S is decreasing, the sign of delta S is negative. So if we go back to this equation, the 2NO plus O2 goes to 2NO2, has a delta S that is negative, and the CO2 solid going to CO2 gas has a delta S that is positive. There is one equation for entropy that you should be aware of. If you have an isothermal process, that is, T is constant. Isothermal. T is constant. You can say that delta S of the system is equal to Q of the system over the temperature, and that's a Kelvin temperature. Or conversely, delta S of the surroundings is negative Q of the system over temperature. Again, temperature has to be a constant. This is an isothermal process. Another thing to remember about delta S is it's a state function. Remember what that means. That means we can calculate it without worrying about the path. So remember that lovely equation, the one with the summation signs in it, that says you can add up all of the delta H's for the products and subtract all the delta H's for the reactants and get the delta H for the whole reaction? Well, you can do the same thing with delta S. You can say that delta S for a reaction is equal to the summation of N delta S of the products minus the summation N delta S of the reactants, which is why when you looked up those delta H values, there were also delta S values in that table. You can do exactly the same things with delta S that you did with delta H.